in the summer of 1968, you went to the cinema in the UK to watch this odd little movie titled 2001: A Space Odyssey. Partly inspired by that movie, partly inspired by the space race of that decade, and partly inspired by this book cover of this random book, Statistical Physics, Volume 5, you started falling in love deeply with physics first, and then with computation, and then with the fundamental theory. I want to start there. I want to start with why. Why do you think you gravitated towards these super easy questions when teenagers your age had so many different interests? Why were you naturally inclined towards finding the machine code of the universe and the fundamental theory for existence?
Well, I didn't expect to be finding the fundamental theory of physics until much later. What I was interested in at first was actually the future mostly. Yeah. And it was kind of a thing where there is the life one's leading and there is things one imagines might be possible. And seeing movies like 2001 gives one the idea of what might be possible. And so that was at first the thing that I was most interested in, is kind of what might be possible. And then I got, at that time, as the 1960s, space was the big thing, and it was kind of all these spacecraft, and they were kind of the pinnacle of technology at the time. And so I followed these things quite closely. And then I got interested in, okay, what would it be like if you were to design a spacecraft? How would that work? And what were the issues in doing that? And that led me into physics. And then I got interested in physics and started learning about physics. Now, I have to say, I mostly ended up asking these questions. I would read something about physics, some physics textbook or something, and then I would wonder, what's the story with this? What's the story with that? I don't think I internalized the fact that many of the questions I asked did not have known answers. I mean, I kind of didn't really make a distinction between the things where the answer was in the back of the book and the things where nobody knows the answer. That wasn't it was something where, for whatever reason, I was just like, I kind of can think about things and can figure things out. And that was kind of what I was interested in doing. Now, my interest in physics at first was a time in physics when lots was happening. This was kind of late 1970s. There was kind of the golden age of quantum field theory-based physics. And so, as a teenager, it was kind of cool to be sort of running with the pack, figuring things out about quantum field theory. And, it's kind of nice when thing you invent when you're 17 years old still gets used, however many years later and so on, which is what happens if you're in a field where sort of there's low-hanging fruit to be picked and the kids can pick the fruit, so to speak. And I ended up being in that position. Yeah. But then I got... I was sort of lucky enough to get to the point where, I got my PhD when I was 20, and I was basically a physics professor, which had been my kind of goal for the decade before that. That was my goal. Yeah. And then sort of you get to the point where you've achieved that goal, and then it's okay, so what's next type thing. I could do, I was like, that was what I was planning to do. So I could do this for the rest of my life. But I was kind of, it's like, well, there are these questions that I'm interested in. What can I figure out about them? And again, the question that I was most interested in at first had to do with kind of what makes complexity and structure in the universe. There's something where you can ask about it in terms of, what makes kind of the structure of galaxies and planets and all that kind of thing. What makes kind of the patterns of snowflakes, those sorts of things. The question was, are there general things that you can say about how structure and complexity gets made in the world? And so I got interested in that. As a practical matter, I had used computers a bunch, and I had built, by that point, my first big computer system, kind of first computer language. And it was an interesting experience building a computer language because, when you do natural science, you're kind of starting from the world as it is, and you're trying to kind of drill down and see, what's that world made of. When you make a computer language, you're starting from something you completely invent for yourself, and then you're trying to build something, and you hope that it's useful in the end. And so that gives one a slightly different perspective on how one thinks about doing science. Instead of doing the kind of drill down from what we know, it's more, let's see what's fundamentally there and try and build up from that, and then see whether what we get is something that corresponds to things that we actually observe in the world and so on. Yeah. And so beginning of the 1980s, that was kind of the thing that I got interested in doing, was, take these like very simple programs, sort of little creatures in the computational universe, see what they do. And then the big discovery, which actually was, I realized that one of the main things that happened with that happened exactly 40 years ago yesterday. So, which was this question of, when you have a simple program, a simple set of rules, what kind of behavior does that produce? Mm-hmm. And what I had assumed was simple rules, simple behavior. This turns out not to be true, which is what I discovered by doing computer experiments. And sort of I had actually done several computer experiments around 1981, and it took until 1984, until June 1st, 1984, actually, for me to realize that, these things that I already did, they have a significance that's quite different from what I thought they had. And so that kind of launched this idea that from very simple rules, you can sort of create very complicated behavior. And that was a thing that kind of has been a theme in my sort of adventures for the last 40 years or so. Yeah. I think that the thing that, it's been an important thing for me that I've kind of alternated between doing these kind of basic science, sometimes almost philosophical kinds of things, and doing practical technology development, because turns out the basic science informs what you should do and how you should do it in the technology development. And the technology development then gives you tools, which if you use them correctly, let you build more basic science. And that's been in the arc of my life, so to speak, that's been a very important thing. But in terms of sort of the what is foundationally there, the question of that for physics is one that I poked at a number of times. But if you'd asked me in the 1980s, will the things you're doing figure out how physics fundamentally worked, I would say I don't see how that will happen. But what I knew was that these things that I was figuring out would explain a bunch of features of kind of the larger scale world, and sort of how snowflake patterns are produced, how turbulent fluid flow works, these kinds of things. But not, if you say, what's at the foundation of physics, what's at the foundation of reality in nature, I would have said, I don't know how that's going to work. Yeah. And then at the beginning of the 90s, so I developed this thing that's now Wolfram language, Mathematica, big software system, gets used by lots of people. That system, one of the things that was sort of the big idea in developing that system and its predecessor actually was that one should do this sort of natural science-like thing of drilling down from sort of all the computations people want to do and say, what are the underlying primitives? What are the atoms of computation? Yeah. And then build up from that and make a practical system. Anyway, I had done that, and I'd sort of gone back to doing basic science kinds of things. And then I thought, well, I should just think about this physics question. Yeah. And the big issue there was sort of what is space and time made of? Yeah. And so, I had studied a lot these computational systems that have kind of rigid view of space. There's a bunch of cells laid out in a line, let's say. And I knew that wasn't something that would be the way that physical space works. And so I started thinking about physical space as this kind of network of points where there isn't really a way of describing. There's not sort of a rigid lattice of cells. Instead, it's just this network that says this point is related to this point in this way, and so on. And so I started studying that, and I got a certain distance with that. And by the end of the 90s, actually, I had figured out that much as, when you look at a fluid, for example, with a bunch of molecules bouncing around, we know that those individual molecular collisions on a large scale give you the fluid equations. Mm-hmm. So I had figured out that when you do the same kind of thing with these networks and the dynamics of these networks, then on a large scale, you get the Einstein equations, the equations that describe the structure of space-time. Mm-hmm. So I knew that by the end of the 90s, and that was interesting. Yeah. And I wrote this big book called The New Kind of Science, and which is mostly about kind of how one takes another step in the trajectory of the development of science based on thinking about programs rather than thinking about mathematical equations as kind of a foundation for how to talk about nature. But as one sort of use case, I had one half of one chapter that was about the fundamental theory of physics. Yeah. And my friends in physics hated that chapter. And which was a sort of interesting thing, because it was a time when kind of there was string theory and my friends in physics said, we're almost there. We've almost got the fundamental theory of everything. And, we don't really need, don't distract us with something else. So when that was, so I did a little bit more work on that beginning of the 2000s. But I didn't really pursue it that energetically, partly because there was a bunch of technology that ended up being pretty important that I was interested in developing and was also pretty intellectually interesting. But then in 2018, I kind of had always thought at some point in my life, I should work again on this fundamental theory of physics stuff.
Yeah.
And, but I'm getting older and it's kind of like the time is visibly limited, so to speak. And eventually it was 2018. I kept on thinking about it a bit, and I made a little technical piece of progress in 2018. And then we do this summer school every year, and a couple of young physicists were at that summer school, and I'm telling them about this progress, and they're like, you can't just not do anything with this. Yeah. You got to actually, pursue it. So I was like, okay, if you help me do this, I'll see what I can do. And so in late 2019, started really digging seriously into this question about sort of what's the universe made of, and can we understand it computationally? And it was really surprising, because I thought it would take 50 years to get to certain places in terms of the level of understanding we have. And it didn't. It happened really quickly. It was kind of like, once you kind of poke at it in the right way, everything starts falling out. And which was really exciting. And actually it was not what I was expecting to have happen at this point in my life, but it's really neat. And in addition to understanding a lot about physics, it's kind of led to a lot of other kinds of understanding of other fields and kind of philosophical understanding of lots of things. Yeah. It's a very, very fertile, exciting moment. I think if you look at the arc of sort of the history of physics, there was a very, the beginning of the 20th century was a time of great progress in physics. The three big theories of physics that we have today, general relativity for gravity, quantum mechanics, and statistical mechanics, the second law of thermodynamics, and so on, those were all kind of put in place basically at the beginning of the 20th century. By the way, ironically enough, at that time, most people thought that space was discrete, but nobody could actually make that work. And 100 years later, we finally have the tools needed to make that work. And it turns out it seems to be true. We don't know yet for sure. Hopefully within a few years, there might be experiments that can validate the fact that space is discrete. It's kind of like matter. People had argued since antiquity, is matter continuous or discrete? Are there atoms, or is it just sort of a flowing thing? And then by the beginning of the 20th century, it's like, yes, atoms and molecules really exist. People were sort of lucky in the fact that the sizes of molecules are such that the experiments that could be done by the beginning of the 20th century could detect things of that size. Yeah. We may or may not be lucky with the discreteness of space, whether the kind of the elementary length, the shortest distance that can exist in space, whether that is big enough, or whether we're clever enough to figure out some way to make sort of a space-time microscope to detect it. It's not obvious when that will happen, whether that's something where, it could be that there are sort of mysteries of astrophysics that as soon as we know how to put the pieces together, it'll be like, this is why that happens that way. And, now we can see this is how it all fits together. I don't know that that's going to be the case.